Okay, welcome back, everybody. So I linked the section on Laplace transforms from the online notes in the chat. So have a look at that because a lot of what I say when I start actually computing uh, some of these Laplace transforms and inverse Laplace transforms is going to refer to the table. Um, so we were trying to tidy up yesterday uh, kind of this list of properties that our Laplace transform has. So um, we had mentioned uh, the fact that it's linear is a big one. So we were able to compute these basic Laplace transforms of, like exponentials, cosine, and sine. And from that, and the fact that it's linear, we were able to actually, we got the fact that cosine and sine had the Laplace transforms that they do from linearity. So we've already used this property of linearity to make our lives easier. So that's just one example of this. Another, as we mentioned previously, is this fact about multiplying by exponentials leading to a shift in the Laplace transform. And then the opposite, right? Laplace transform of a shift in this sense, where use the Heaviside function, leads to multiplying by an exponential. So multiplying the Laplace transform by an exponential. So that is kind of a nice sort of like duality thing there between translations and exponentials that Laplace transforms have. So that's one. That's just one way in which this is basically making our lives easier. So there's a few more. There's a few more that I want to talk about. A few more properties that are going to be very important. So the first one, so you can call this, I think we were labeling them prop. So we're on prop 4 now. This is something we've encountered before in our first two examples of Laplace transforms we computed. We actually showed a version of this, which is the following. If I take the Laplace transform of t to the k times some function f of t of s. And we're going to assume all the regularity here required is okay. You'll see what I'm saying here in a second. So if I take the Laplace transform of t to the k f of t, what is this? It turns out that an easy way to compute this in terms of the Laplace transform of f is that this is minus 1 to the k times the Laplace transform, or sorry, times the kth derivative of the Laplace transform of f. This is introducing some notation that is going to be pretty common throughout. So this, where f of s is the Laplace transform of little f. So using an uppercase letter to denote the Laplace transform of the corresponding lowercase letter function is very, very common notation that we're going to be using throughout this chapter. So in the context of Laplace transforms, when you see this, you can go ahead and assume that that's what's going on. Whenever you see a capital letter, you can assume that's the Laplace transform of the same function that has that letter as that's the lowercase version of that letter is denoting that function in question. So how does this work, and how have we seen this before? So recall that the Laplace transform of t e to the at was what? What was this? So remember, this was actually 1 over s minus a squared, right? And the Laplace transform of e to the at of s was 1 over s minus a, right? Well, note, if this is if little f here is e to the at, Right? That's little f of t. Then I'm calling this big F of s, and if I take the derivative of that with respect to s, what do I get? I would get minus 1 over s minus a squared, right? So then minus 1 to the 1 times f prime of s is 1 over s minus a squared. But that's Laplace transform of t e to the at of s, right? So that shows how these things are related. So I hinted when I first showed you this that, when you have t e to the at is 1 over, there's a Laplace transform, this is 1 over s minus a squared. How did that compare here? I said it's not, you might say, oh, you just square the denominator, right? But that's not really what's going on here. What's actually going on here is you're multiplying by t is taking a derivative. Okay, that's kind of a way of thinking about it intuitively. So multiplying by t in the Laplace transform takes a derivative. That's the way to think about what's going on. So every power of t that I multiply f by takes another derivative. And yeah, there's this minus 1 to the k out front here, but forget about that, right? That's something you toss in at the end. This is the main thing to think about, is that multiplying by t is associated with taking derivatives of the Laplace transform. Okay, so this is another fact that gives you a ton of new ways of computing Laplace transform. So for instance, what about, let's see some examples of how this helps fill out the table even further. So let's do the Laplace transform of just t to the k of s, right? Well, what is that? Well, really, this is the Laplace transform of t to the k times e to the 0 t of s, right? But what's the Laplace transform of e to the 0 t? Right? Of course, you might say this is a really funny way of writing the Laplace transform of 1, right? But following our formula, Laplace transform e to the at, remember, Laplace transform e to the at is 1 over s minus a. So if a is 0 here, this is just 1 over s, right? So this is just 1 over s. Okay. So then, what is this? Laplace transform of t to the k, that's Laplace transform of t to the k times e to the 0 t. So this is like minus 1 to the k, right? Whatever that is. So this is like minus 1 to the k times what? So this is going to be, what am I going to be multiplying here? Since I'm taking a kth derivative, I'm going to get descending powers of s here. So I'm going to get k factorial over s to the k plus 1. Right? So when I've taken the kth derivative of 1 over s, I get 1 over s to the k plus 1. And this k factorial is coming from taking these successive derivatives, right? So there we go. Okay, of course, I could immediately compute Laplace transform of, say, t to the k e to the at now, instead of just t to the k. So following the same thing, this is k factorial over s minus a to the k plus 1. Now you might say, oh, there's another way I can actually see what it is that's going on here, right? And that other way is to say, well, I know the Laplace transform of t to the k. Multiplying by e to the at is a shift, right, by a. Oh, so it takes this and replaces s with s minus a. That's one way of viewing it, right? Of course, I could also just view this as, oh, it's the minus 1 to the k times the kth derivative of this, or of 1 over s minus a, which is this thing. So either way you want to look at it there. Okay, and so on. So those are just two examples, but this is showing you how this fills out the table. Now, the next property is extremely important. Okay, so I'm going to put stars next to it. This is important enough that technically you are going to use this in every Laplace transform problem. So we'll use in every Laplace transform problem. Okay, so what is this? So this tells you how the Laplace transform transforms derivatives of an unknown function. So here is the first fact. So this prop 5 can be thought of as like a list of facts. So the first one, right? How does Laplace transform the derivative of a function? So f prime. So the Laplace transform of f prime of s is s times the Laplace transform of f of s minus f of 0. This is the first one that is important. I can use this for higher derivatives. Okay, so the next one, technically I can keep doing this for any order, but I'm only going to do a couple of these. So the second one, Laplace transform of f double prime of s. Well, I can think of f double prime as being f prime prime, right? So then really what this is this is s times the Laplace transform of f prime of s minus f prime of 0. Right? But the Laplace transform of f prime by this first thing is s times Laplace transform of s minus f of 0 minus f prime of 0. Simplifying this, this is s squared times the Laplace transform of f of s minus s times f of 0 minus f prime of 0. These two are the most important. I can keep going, but I'm not going to. Okay, so there's more of these, but I'm not going to do them because we are meaning to apply this to a second order equation, and so these two are the only ones we actually need. But there are similar formulas using both of these for f triple prime and so on. So I can keep doing this, but I'm going to stop here. These are the two I need. Now, this is extremely important because this is going to show us how we are going to be able to solve these problems, these problems involving Laplace transforms. Okay, so how does this work? So, as I drew this picture last time, this is a very important diagram because this really explains what it is that's going on with these problems. So I have an IVP. That IVP is a differential equation L of y is equal to f of t plus initial conditions, right? Okay. All right. So I want to solve this. I want to have a solution. So solution to IVP. And we call this solution little y, right? Okay. Now you've already seen in order to do that, I take, using Laplace transforms, I take this IVP, I hit it with the Laplace transform. What I'm going to do then is use these two facts. Okay, I'm going to use these two boxed facts to transform this equation, Ly is equal to F, into an algebraic equation that looks like this. P of s, where p is some polynomial, times big Y of s, where big Y of s is the Laplace transform of little y, minus Q of s is equal to big F of s, where P of s is the characteristic polynomial of L. Big Y of s is the Laplace transform of little y of t of s. Q of s is some polynomial. So Q of s is some polynomial depending on initial conditions. And big F of s is the Laplace transform of little f of t, the right-hand forcing function of s. We'll see how this breaks down. Okay. This algebraic equation, of course, has the same solution every time. What do? I take big F, I add Q of s to both sides. So on the right-hand side, I have f of s plus Q of s. On the left-hand side, I have P of s times Y of s. Divide both sides by P of s. I solve for big Y. So here, I solve for big Y. Big Y is the Laplace transform of little y. So I solve for big Y, which leads me to an algebraic solution to this equation, which is big Y of s is equal to f of s plus Q of s over P of s. So what I have done in this process is I started with an IVP looking for an unknown function little y that solves this IVP, so this differential equation plus these initial conditions. What I did was I hit that IVP with a Laplace transform, solved the resulting algebraic equation for an algebraic solution, big Y of s. So what I did was instead of finding little y, I found big Y, which is not little y, it's the Laplace transform of little y. But what I really want is little y, not big Y. Well, how do I go from big Y to little y? Here's big Y. How do I go to little y? I have to hit it with the inverse Laplace transform. We'll see how that works. Okay. So I have to hit it with the inverse Laplace transform. And this completes my solution here. Okay, so this is my roundabout way of solving this using Laplace transforms instead of some other method. Okay. Now, this might seem a little bit abstract to phrase it this way, but I think it's important to see how this general process works, because I think it is important for you to understand that this always works the exact same way. So all that is left for you to do, like this process is totally determined. All that's left for you to do is actually compute these things. Typically, the hardest part of this process is finding big F. Computing this Laplace transform, this is typically the hardest part. So this is typically the hardest part of this process. Okay. So for instance, when when you're doing this for like a homogeneous equation, right? If you would ever want to do it for a homogeneous equation, this would be easy. This would be made simple. Of course, for a homogeneous equation, we're not typically going to use Laplace transforms because why would you? You know how to do it otherwise. But this is just to illustrate how this is done. Okay, in fact, the first example that I do will be of a homogeneous equation, just so we can nicely check our work here. Okay, so let's do an example here to actually see how this works. Okay, so let uh, let's let say y of t be solution to the differential or the IVP, say y double prime minus 2y prime minus 8y is equal to 0, with y of 0 being equal to 3 and y prime of 0 being equal to 7. Okay, so two steps. One, find y of s, which is the Laplace transform of y of t of s. And secondly, find little y of t. Now, bringing back my diagram here, I left some space for little y of t. If I've hit this with the the inverse Laplace transform, little y of t can also be thought of as the inverse Laplace transform of big Y of s of t. You see how the roles of s and t are swapped here? That should be expected since this is an inverse thing, right? So this is acting, going in the other direction. Okay. All right. So, I want to find y of t, i.e. solve the IVP in question. So I'm breaking this up into two pieces because when these examples are done in the online notes, typically the way these are done is like a bunch of examples will be done where the only thing you're asked to do is to find the Laplace transform of the solution. And then, to actually fully solve this, of course, you would need to then hit that with the inverse Laplace transform to get the actual solution out. So that's what we're going to do. We're going to do both parts here, not just one. Okay, so these are split up typically, like I said in the online notes. Usually when they go through the examples the first time, they'll just do the first part, and then they'll revisit those same examples and do the second part, actually solving it. We're just going to do both of these at the same time. Okay, and so what do I do here? Well, let's look at my process again. What does this say to do? I start with an IVP. I hit it with the Laplace transform and get an algebraic equation. So let's do that part. Okay. All right. So this is a homogeneous equation. I'm going to hit it with a Laplace transform. So this is the Laplace transform of y double prime minus 2y prime minus 8y is equal to, and that's of s here, is equal to the Laplace transform of 0 of s. Okay. All right, and so what this is using linearity of the Laplace transform. This is the Laplace transform of y double prime of s minus 2 times the Laplace transform of y prime of s minus 8 times the Laplace transform of y of s is equal to the Laplace transform of 0 is 0. So there we go. Okay. Now what do I do? So here I use linearity, right, to break this up. This is a linear thing itself, so all this is going to be respected and it's going to be nice. Okay, now what do I want to use? So I want to use the formulas for how the Laplace transform transforms the derivative of a function. So Laplace transform of f prime is s times the Laplace transform of f minus f of 0. Laplace transform of f double prime is s squared times the Laplace transform of f minus s times f of 0 minus uh, um, minus f prime of 0. Right, so that's how this works. Okay, so let's see what I want to do here. First of all, we do the replacement, right? Big Y of S is the Laplace transform of little y of t of S. And so there is big Y, for instance. So we're trying to put everything here in terms of S and big Y of S. Okay, so Laplace transform of y double prime. Maybe I'll just bring my facts back here. So Laplace transform of y double prime, just using this formula, is what? Laplace transform of y double prime is s squared times the Laplace transform of y of s, but the notation I'm using for that is big Y. So this is s squared times big Y of s minus s times y of 0 minus y prime of 0. So that whole expression comes just from this, right? So this alone leads me to this expression. Minus 2 times the Laplace transform of y prime. Well, using this formula, this would be 2 times s times the Laplace transform of little y, which is big Y. Right? So this is s times big Y of s minus y of 0. Okay. So that's what I get from this. Here, this would be minus 8 times Laplace transform of little y is big Y. So this is 8 times big Y of s, and that is equal to 0. So there's an example of how we use this fact. Okay, so this is how we use this fact that we know how the Laplace transform transforms derivatives. Okay, now let's do some simplifying here. So and group all of the things that have a y of s in them and group the other terms separately. So this is an IVP. Y of 0 is 3 and y prime of 0 is 7. So rewriting this, this would be s squared minus 2s minus 8 times big Y of s. Just check. Ys times s squared. Yep. Ys times minus 2s. Yep. And ys times minus 8. Yep. Okay, so that takes care of that term, and that term. So then what is left? I have minus s times y of 0. So y of 0 is 3, so this is minus 3s. So that takes care of this term. Minus y prime of 0. Y prime of 0 is 7, so this is minus 7. Okay, that takes care of that term. Now I have minus 2 minus y of 0, so that's plus 2 times y of 0 is 3. So that takes care of that term. Okay, and I think that does it, right? That's every term here, and that's equal to 0. Okay. All right. What do you notice about this? S squared minus 2s minus 8. What is that? It's the characteristic polynomial, just with s replaced instead of z. So actually, this is the characteristic polynomial. This always works out this way. That's the characteristic polynomial. So what do I get here? I get y of s. I get s squared minus 2s minus 8 times big Y of S is equal to, this is plus 6, so this is minus 3S minus 1 here. So this is equal to 3S plus 1. I've now moved this to the other side. And now I divide both sides by P of S, or by the characteristic polynomial. And so big Y of S is 3S plus 1 over S squared minus 2S minus 8. So I have solved for my characteristic polynomial. Or sorry, not my characteristic polynomial. I've solved for my Laplace transform of big Y. Okay. Now, I've done the first part, right? That's what I was asked to do. So find big Y. Big Y is this. It's 3S plus 1 over S squared minus 2S minus 8. Now, how do I go from this to little y, to the actual solution to this differential equation? Well, if I go back to my process, I go from here to little y by hitting it with the inverse Laplace transform. So now it's time to talk about the inverse Laplace transform. So here's a little aside. How do I compute inverse Laplace transform of, we'll say, big Y of S of t? How do I compute this? The answer is to read the Laplace transform table backwards. What do I mean by that? So refer to page 14 in the notes in chapter 2, section 9. So I linked those in the chat. So look at page 14. So for page 14, let's just have a look at some of the lines here. Okay, I'm just gonna copy some of these lines down. All right, so I'm gonna copy some of these. So I'm gonna say, okay, like I'm not gonna copy all of them. Obviously, there's too many of them. So I'm just gonna copy a few. So let's do like a Laplace transform of t to the n of s is n factorial over s to the n plus 1. So that's one of them, and this is for this is for s greater than 0. Yeah, I'm not going to write these from here on. You can look up those lines in the table if you want to see which are good and which are not. Let's do Laplace transform of cosine of bt. Right, so what is this? Well, we saw already this is s over s squared plus b squared. And Laplace transform of sine of bt of s is b over s squared plus b squared. And if we do, say, Laplace transform of, let's say we do like the Laplace transform of like e to the at cosine of bt, right? Remember, this is a shift. This is a shift by a, so this turns this from s over s squared plus b squared to s minus a over s minus a squared plus b squared. So that's exactly what I get here. Okay. Similarly for sine b, if you like. So Laplace transform of e to the at sine of bt of s is, I'm taking this and shifting it by a. So this is b over s minus a squared plus b squared. And of course there's more. Okay. But this is a tiny table. Okay. So this is an example of a table, meaning that you have a Laplace transform of something you're trying to compute. So in this case, t to the n cosine bt sine bt, e to the at cosine bt, e to the at sine bt. And you just read off what the Laplace transform is from this table. Now, we computed a lot of these, right? We actually showed why these were equal to this. But you don't have to do that from now on. You can actually just refer to Laplace transform table. Okay. So what you're going to do is you're going to want to separate everything that you can when you're trying to compute a Laplace transform using linearity, so these properties of Laplace transform, into something that you can just read off from the table. So maybe it's a bunch of pieces, or maybe it's a bunch of terms, but each of those terms is something here. So what I mean by reading forward in the Laplace transform table is just reading this as it says. The Laplace transform of t to the n of s is n factorial over s to the n plus 1. What do I mean when I say reading backwards? So a Laplace transform table is nice because I can read it forwards and backwards. To read it backwards, to compute the inverse Laplace transform, I simply take the thing on the right as the thing I'm taking the inverse Laplace transform of and say, well, here, let's do it like this. I'll write it on this piece of paper. So here's my Laplace transform table. How do I read this table backwards? Well, what I do is I think of making an inverse Laplace transform table from this. I take the thing on the right instead. So the inverse Laplace transform of n factorial over s to the n plus 1 of t. What is that? It's the thing you're taking the Laplace transform of on the left. So if reading the table forwards is reading from left to right, like you normally do, reading the table backwards is reading from right to left. So the inverse Laplace transform of n factorial over s to the n plus 1 is t to the n. Let's do it for the next line. The inverse Laplace transform of s over s squared plus b squared of t is cosine of bt. I don't have to do every single one of these. Let's skip to this last one. The inverse Laplace transform of, say, b over s minus a squared plus b squared of t is equal to e to the at sine of bt. So this is what I mean by reading backwards. This is how to write the inverse Laplace transform. A couple of things to note. The Laplace transform is linear. So is the inverse Laplace transform. This is actually very important because what it means is that you can use this fact to split up the thing you're trying to take the inverse Laplace transform of into pieces that make it more manageable. Okay? So that's the idea here. Okay. So doing the algebra involved in this is something that you're probably going to find to be a little bit tricky the first time you do it. But this is key to kind of understanding what it is that's going on here. And once you get the hang of it, you'll see, what is meant by all of this. So let's do an example. Okay, well, the example makes sense to actually do the thing that we want to solve here, right? So for instance, boom. Right, so so this is my example continued. So big Y of S is 3S plus 1 over S squared minus 2S minus 8. Okay. And I want to find Y. Little y of t, which is the inverse Laplace transform of big Y of S of t. How do I do that? Now, ideally, this would just be something in the table, right? And it would be as easy as literally reading it off, right? So it would be as easy as saying, oh, well, there it is in the table, and I want to go in the opposite direction. I want to go in reverse, right? I want to read it off like this and just be done. But the problem is that if you look at that table, right? So this is page 14 in chapter 2, all right, section 9. So if you look at that table, this doesn't look like anything that's on the right-hand side. So here's a shortened version of that table just to show you. Are any of these, right? Are any of these, do they look like this? Right, so there's big Y. Let me put this over here. Does this look like anything in this table? Like I said, this is a shortened table, but the other things in that table are not going to factor in here anyway. So in this shortened table, this should be enough to do this. But is it apparent, right, immediately that this thing is equal to one of these things on the right? No, right? So the problem with the inverse Laplace transform is that it is precise in the sense that like these things have to be exactly of this form. Like just being kind of this form is not enough, right? This is a quadratic in the denominator. It's an s squared something, but it's not in this exact form, so I can't take its inverse Laplace transform. So what do I do here? I want to put it in some form that shows up here. I want to put it in some form that is going to show up here. What does this look like? So first of all, you might notice, oh, well, this thing factors, this denominator. So I could rewrite this as 3s plus 1 over, how does that factor? This is like s minus 4 plus 2, right? So this is s minus 4, s plus 2. Well, still, does that look like anything in this table? Right, does this look like anything in the table? Well, no, right? No, it doesn't. What do I do here? Well, what if I had this thing written in the following way? What if I could write this as big A over, say, s minus 4 plus big B over s plus 2? What if I had this? Would I be happy? All right. Just theoretically, right? Just theoretically, let's say that this is the case. So ignore this for now. If we could rewrite this in this fashion, am I happy? What would the inverse Laplace transform of that thing be? So what's the inverse Laplace transform of this thing? Inverse Laplace transform is linear, so this would be A times the inverse Laplace transform of, and where A and B are constants here. So A times the inverse Laplace transform of 1 over s minus 4 of t plus B times the inverse Laplace transform of 1 over s plus 2 of t. Can I find the inverse Laplace transform of these things? Well, I didn't write it as a direct entry in this table. It's hidden, right? So if I take b equal to 0, right, so that this is the Laplace transform of e to the at, I get s minus a over s minus a squared, so 1 over s minus a. But just reminding myself, the Laplace transform of e to the at of s is what? It's 1 over s minus a. And so from this line, what is the inverse Laplace transform of 1 over s minus a of t? Well, I'm going backwards now, so this is e to the at. So the inverse Laplace transform of 1 over s minus a is e to the at. So if that was the case, this is a times e to the 4t plus b times e to the minus 2t. And I would be done if I could find out what these constants were. There's a lot going on here. So what's one thing? Notice you already knew that this was the form that this had to take. Why? Remember the equation this came from. Here's the equation. Its characteristic polynomial is s squared minus 2s minus 8, which factors in this same way. So it has roots 4 and minus 2. Right, so so p of z has roots z equals 4 and minus 2. So we already know that this is a homogeneous equation. We already know that y of t from this is, c1 e to the 4t plus c2 e to the minus 2t. So we already know the general solution to this equation is this. And then we're given these, right, initial conditions, so we could figure out what c1 and c2 are from that. Okay, so we actually already knew that it had to be in this form. All right, but say that we didn't know that. We have shown that so long as this can be split up in this way, I can find this. Well, what is this? Can I do this? This is just called the partial fractions decomposition. It's just the partial fractions decomposition. That's it. Okay, so you are going to, in general, need to use partial fractions in order to make all this stuff work out. That's just something that is going to happen. Okay, so let's do that to actually figure out what this a and b are. So 3s plus 1 over s minus 4 times s plus 2. I'm going to write that as a over s minus 4 plus b over s plus 2. Now, there's a lot of different ways you can do partial fractions decomposition, right? There's some cheating ways you can do that doesn't always work depending on the degree of the denominator here compared to the degree of the numerator. However you want to do that, however you were taught, so long as you are following the rules here. If I clear denominators, right, so if I multiply both sides by s minus 4 times s plus 2, I get 3s plus 1 is equal to, this would be a times s plus 2 plus b times s minus 4, right? So then setting these things up properly, 3s plus 1 is equal to a plus b times s plus 2a minus 4b. Comparing the coefficients here, since this is 3 times s, a plus b has to be equal to 3. And 2a minus 4b has to be equal to 1. So these have to be, of course, satisfied simultaneously. Okay. So then, what's a way of doing this nicely? So let's see here. Let's multiply, say, both of these by 4 and add them. So if I multiply a plus b equals 3 by 4, I get 4a plus 4b is equal to 12. I add those together and I get 6a plus 4b minus 4b is 0, so I get 6a is equal to, so 12 plus 1 is 13. All right, so this is equal to 13. So a is equal to 13/6. Well, if a is equal to 13/6 and a plus b is equal to 3, then b needs to be equal to 5/6 so that this is 18/6. So this implies that b is equal to 5/6. And so it turns out our inverse Laplace transform, we can just rewrite it right here, is 13/6 e to the 4t plus 5/6 e to the minus 2t. And that is it. Now, I want you to notice a couple of things in this process. Okay. So the first thing to notice, notice that I never, like, even though I had found this kind of general form this thing had to take, that was just me showing you how this worked. In general, you would just do this partial fractions decomposition immediately, right, if you needed to. So you would do it, and then this would just pop out. So unlike our previous method of solving this, right? Now I know this is a homogeneous equation, so you're typically not going to use Laplace transforms here. But just to show you how this works, if you were doing this the old way, you would first find the general solution, which you know because it's homogeneous, so there it is. And then you would impose the initial condition. So you would plug in 0 here and set that equal to 3. You take the derivative of this thing, plug in 0, set that equal to 7, and then solve for C1 and C2. Notice that I did not have to do that here. These automatically popped out. Okay, so that is one cool thing about the Laplace transform, is that when you do this process, the solution automatically pops out here. Like the unique solution automatically pops out. These constants are automatically determined by this process. So you don't have to impose any initial conditions in that sense. It just automatically works. It just automatically pops out from the previous algebra that you did. So that's one cool thing about Laplace transform. There's no need to do any. It will like automatically pop out the unique solution, and you don't have to do anything further. Okay, let's do another example. Let's see here. So let's do another example here. Let h of t be a solution to the IVP. Now, we know that, of course, this is not a solution. This has to be the unique solution. Let h of t be the unique solution to the IVP. H double prime plus 4h is equal to sine of 3t. Okay, and let h of 0 and h prime of 0 both be 0. Okay. So again, find big H of S, which is defined to be the Laplace transform of little h. And 2, find little h of t. We're going to do that, of course, with the inverse Laplace transform. All right. So what's the process here? Process here is the same as always with Laplace transform problems. I hit this equation with the Laplace transform. So this is a Laplace transform of h double prime plus 4h, right, of s. And that is equal to the Laplace transform of sine of 3t of s. Okay. All right, so how does this go? First of all, here I use linearity. So this would be L of h double prime of s plus 4 times L of h of s, and that is equal to, what's the Laplace transform of sine of 3t? We have that in a table, right? So we can look at, you know, the full table like was presented on page 14 of that section, or look at this truncated table that I've drawn out here. So Laplace transform of sine of bt is b over s squared plus b squared here. So this is Laplace transform of sine of 3t. So that is going to be 3 over s squared plus 3 squared, or s squared plus 9. So this is going to be 3 over s squared plus 9. Now you might say, well, you said that was typically the hardest part, and that was really easy here. That's true. It's easy for this case. But in general, for a more general forcing function, the right-hand side function, this finding Laplace transform of that is going to be harder usually than most other parts of this. So here I use the same fact that I always do, right? So this L of h of s is, of course, big H of s. That's what we use this for. The Laplace transform of h prime of s is s times big H of s minus h of 0, which in this case, because h of 0 is 0, this would just be 0 here, so this would just be s times h of s. And then the Laplace transform of h double prime of s is going to be s times h, so this is Laplace transform of little h prime of s minus little h prime is 0. So this would be, this is just going to be s times big H of s. So this is going to be s squared times big H of s. Little h prime of 0 is 0. So this is s squared big H of s. Now putting all those together, right? Putting all those together, this gives me up here s squared big H of s plus 4 times big H of s is equal to 3 over s squared plus 9. Factoring out an h of s from both sides, or sorry, from both terms here, this is s squared plus 4 times big H of s is equal to 3 over s squared plus 9. So one thing to notice, of course, is s squared plus 4 is the characteristic polynomial for this thing, right? Characteristic polynomial is z squared plus 4. So it's just the characteristic polynomial with s plugged in. This always has to work like this, just like it worked in the previous problem. So this is one way of checking that the algebra you're doing is staying on track. At this stage, right, you should have that characteristic polynomial showing up in the same way. Okay, and so to solve for big H, I'd just divide through by s squared plus 4. So big H of s is 3 over s squared plus 4 times s squared plus 9. Okay. So here's again a question, right? A question is, well, like, do you see anything in our table that looks like when I mix these together, I should end up with something like, does this look anything like what's on the right hand side? Not really, right? Not really. So what is the idea here? What do I want to do? Well, similar to last time, right, if I'm going to find the inverse Laplace transform of this, so let's rewrite this. Right, so here's my same example continued. So h of s is 3 over s squared plus 4 times s squared plus 9. You might say, well, I don't really remember how to do partial fractions decomposition when I have this kind of thing in the denominator. But really, right, algebraically, these s squareds are the same thing. This is thinking about this just as kind of this rational expression, this fraction. Really, this is like a 3 over, z plus 4, z plus 9 kind of thing. Or you could have written x here, it doesn't matter, right? So this is the expression that I have, where z is s squared. And you know how to do a partial fractions decomposition of this thing, right? So if I were to try to decompose this as like big A over z plus 4 plus b over z plus 9, oh, my 4 and 9 kind of look similar there. There we go. We're going to try to do this sort of thing. What would that lead to? If I clear denominators here, this means that 3 is equal to a times z plus 9 plus b times z plus 4. So comparing the coefficients here, right, I would get 3 is equal to like a plus b times z plus 9a plus 4b. And so this implies that a plus b has to be equal to 0 because there is no z term over here. And 9a plus 4b is equal to 3. Okay. But then a plus b being equal to 0, this means, for instance, that a is equal to minus b, right? So putting a is minus b here, this is this second thing becomes minus 9b plus 4b is equal to 3. So this is minus 5b is equal to 3, or b is equal to minus 3/5. So if b is minus 3/5, then a is 3/5. And so what we have done here is actually shown that, so now, of course, this, it doesn't matter what this c was. This can be rewritten as 3/5 over s squared plus 4 plus minus 3/5 over s squared plus 9. Okay. Okay, and so now I want to compute little h of t. And little h of t is the inverse Laplace transform of big H, which is the inverse Laplace transform of 3/5 over s squared plus 4 plus minus 3/5, I should have just put minus here, but that's fine, over s squared plus 9 of t. Now I kind of see where this is going, so I am going to say this is equal to 3/5, so I'm using linearity here, linearity of the inverse Laplace transform. So this is 3/5 times the inverse Laplace transform of 1 over s squared plus 4 of t minus 3/5 times the inverse Laplace transform of 1 over s squared plus 9 of t. Okay. Now, a couple of things here. One, if I'm looking at this, right, like I'm close to something that's in my table. So let's bring my table back. So I'm looking for inverse Laplace transform of 1 over s squared plus 4 and 1 over s squared plus 9. I'll put that up here. Let's look at my table. Is there anything in this table that looks like inverse Laplace or looks like 1 over s squared plus 4 or 1 over s squared plus 9? This one does. All right, this one does. Well, what's the problem here, though? Instead of having 1 over s squared plus 4 and 1 over s squared plus 9, in this table I have b over s squared plus b squared. So for instance, for s squared plus 4, b would need to be 2 so that b squared would be 4. But I don't have a 2, I have a 1. Similarly, for the s squared plus 9 term, b would need to be 3 in order for b squared to be 9, so that this denominator would be s squared plus 9. Well, that's not too bad. Why not? How can I correct this ever so slightly? Well, what I can do here is I want this to be a 2, and I'm happy. So let's just change that to a 2. But I can't just change that to a 2. In order to correct that, I would have to multiply by 1 over 2. But L inverse is linear, so I could bring that 1 over 2 out. Right? Because this is linear, 1/2 can be brought in. 1/2 times 2 is 1. So I'm back to 1 over s squared plus 4. So adjusting this algebraically is perfectly fine. Let's do the same thing here. I want that to be a 3. So there we go. There it's a 3, but I can't just do that, right? I would have to multiply this on the outside by 1/3. So simplifying, this gives me 3 over 10 times the inverse Laplace transform of 2 over s squared plus 4 of t, minus 1/3 times 3/5 is minus 1/5. So this is minus 1/5 inverse Laplace transform of 3 over s squared plus 9 of t. Now I can read it off directly from the table. Right, boom. There it is. So the inverse Laplace transform of 2 over s squared plus 4 is sine of 2t. And the inverse Laplace transform of 3 over s squared plus 9 is sine of 3t. So this is 3 over 10 sine of 2t minus 1/5 sine of 3t. And that's it. Now, a couple of things that I want you to note. Okay, so first of all, going back, this was the equation that we did. What kind of equation is this? It's constant coefficient, so I can use my Laplace transform. The right-hand side is actually in characteristic form. It's non-homogeneous, but this is in characteristic form. So I would use either key identities or undetermined coefficients to figure out what the solution is, right? So I would solve the homogeneous equation. That's not too bad. There it is, right? It has roots plus minus 2i. So I know that its general solution is c1 cosine of 2t plus c2 sine of 2t. That's the homogeneous part. To find the particular solution, I would have to use either key identities or undetermined coefficients. So I'd go through that whole process, and then my solution would be homogeneous part plus particular solution, and I would impose these initial conditions on it, right, to make sure that all this worked out. Imposing those initial conditions, I would get some values for that C1 and C2, and I'd be done. Well, notice I didn't have to do any of that for Laplace transform stuff, right? I did not involve myself in finding directly the particular solution nor the homogeneous solution. I actually just proceeded, like this, right? I just ignored all that stuff, and I just proceeded in this methodical way of using Laplace transforms. And what I got was, okay, I found the Laplace transform. Once I did some algebra that split it up like this so that I could actually read it off from the table, or read the inverse Laplace transform off from the table, I just did that, right? So I did the algebra again here to massage these a little bit so that they actually agree with the entries in the table. Okay, and then what happens is this solution just pops out, right? So now, looking backwards, we can see that this piece here is the particular solution, and this piece here is part of the homogeneous solution, where that other constant on the cosine term is 0, right? And this one is 3/10. So here's my particular solution, here's my homogeneous part. But notice, I didn't have to do any of that stuff that I did previously in using the method that we would have used to solve this, either undetermined coefficients or key identities. I didn't have to do any of that stuff. I just did the same Laplace transform stuff that I did for the other problem. Okay, so that is kind of the power of the Laplace transform stuff is you follow the same track every single time. There's kind of no deviation there. So assuming you can actually compute those inverse Laplace transforms, or sorry, the Laplace transforms and inverse Laplace transforms, this is how the process works every single time. It works exactly like this. Okay. So those are two good examples of using Laplace transforms to do this. Maybe let's do like one more. Let's do this for like a first order equation, even, just to do it. So let's do something like this. So just to see that we could even do this for our first order differential equations, let's consider the equation y prime minus 2y is equal to e to the 5t. and y of 0 is equal to 3. If I wanted to solve, so this is a first order linear constant coefficient right here, but it's not homogeneous, okay? You know exactly how to solve this. It's already in linear normal form. Okay, so it's already in linear normal form. You could solve this using the methods of chapter 1. No mystery here. But let's just see how Laplace transforms work for this. So hit it with Laplace transform. All right, so this is what I get. Using linearity of the Laplace transform, this is Laplace transform of y prime of s minus 2 times the Laplace transform of y of s. And this is equal to, what's the Laplace transform of e to the 5t of s? This is actually just 1 over s minus 5. This is 1 over s minus 5. Okay, using my fact that I rewrite, this L of y of s is what I'm calling big Y, right? Then the L of y prime of s is s times y of s minus y of 0. Y of 0 is 3 here, so this is s y of s minus 3. Okay. So then what do I get here? So sy of s minus 3. I plug that back into this relationship up here. So this is s times big Y of s minus 3 minus 2 times big Y of s, and that's equal to 1 over s minus 5. Okay. So then I can add 3 to both sides and factor out by big Y of s in the remaining terms. And what I get is s minus 2 times big Y of s is equal to 3 plus 1 over s minus 5. Okay. Now I can divide by s minus 2 here. And what I get is y of s is equal to 1 over the s minus 2 times s minus 5 plus 3 over s minus 2. So that's my Laplace transform of the solution. So now the question is, I want to hit this with the inverse Laplace transform. This is already in a good form. That is in my table. This is not. I need to use partial fractions on this piece. If I use partial fractions, it turns out that 1 over s minus 2 times s minus 5 can be written using partial fractions decomposition as 1/3 over s minus 5 plus minus 1/3 over s minus 2. Okay. So using that fact to rewrite this ever so slightly, this is 1/3 over s minus 5 minus 1/3 over s minus 2 plus 3 over s minus 2. All right. So I can simplify this a little bit. 3 is 9/3, so 9/3 minus 1/3, this is like plus 8/3, right? So this is 1/3 over s minus 5 plus 8/3 over s minus 2. Okay, so that's my big Y of s. So then immediately continuing on here, so my big Y of s, just rewriting it real quick, this is 1/3 over s minus 5 plus 8/3 over s minus 2. If I hit that with the inverse Laplace transform, so this is the inverse Laplace transform of 1/3 over s minus 5 plus 8/3 over s minus 2. Using the fact that this is linear, this would be 1/3 times the inverse Laplace transform of 1 over s minus 5 of t plus 8/3 times the inverse Laplace transform of 1 over s minus 2 of t. Okay. And so these are just directly readable from table. So let's bring the table back. Here it is. Well, the Laplace transform of e to the at of s is 1 over s minus a. So then the inverse Laplace transform of 1 over s minus a of t is e to the at. So you can just directly read off the fact that this would be 1/3 e to the 5t plus 8/3 e to the 2t. And that's it. Okay, so here's another example of how Laplace transform can be used to solve these problems without doing any sort of, I don't need to do any sort of alteration here to the process. Process works exactly the same, whether it's a first order equation, second order equation. It also works just the same for third order and higher. The algebra just gets a little bit more tedious, but the actual process is exactly the same. So we are going to see tomorrow in lecture one special type of equation that Laplace transforms allow us to do that is different. It's something that we weren't basically able to do with other methods nearly as cleanly. And that's the example of your forcing function being a piecewise function. So having a piecewise defined forcing function, that is that's going to be something that the Laplace transform can handle very nicely. Okay, whereas if you were trying to handle this by some other method, it would be really, really nasty if you could do it at all. Okay, so anyway, that's the deal. So then we'll do that tomorrow for probably like the first half of lecture. I'll do an example of that, and then we will be moving on to chapter 3 after that. So then we are headed into the final chapter. I am going to tidy up some stuff in chapter 2. First, I'll talk about Green's functions, which I've ignored until now. So I'll mention Green's functions and some other bits that I'll kind of tidy up from previous material. And then we'll move on to chapter 3. So we'll start chapter 3 by the end of this week, and that's the plan. And then for the rest of the course, we'll be doing chapter 3 stuff with the additional time that we have, because we'll have some extra time at the end. We'll kind of go back and do like an overall review of everything we've done and plug any holes that exist. So anyway, that's the plan. So I will see you all in lecture tomorrow.